When we were talking about integral, we have seen two versions. Indefinite integral, the antiderivative, the primitive function, and definite integral. And there are many different definitions of the definite integral. What we have seen up to now was the so-called Newton's definition of the definite integral. Let me revise that. If we consider integral from a to b of a function f, and when we find the antiderivative, and we evaluate the antiderivative at a and b and subtract, that means at b minus fa, then this is called the Newton's definition of the definite integral. To stress that we mean the Newton's definition, sometimes we write capital N as Newton in brackets in front of the integral sign. So this is the Newton's definition . Not to be confused with the Newton's method to solve algebraic equations. Newton was a pretty hard-working man, and many terms in mathematics bear his name. So this is Newton's integral, and that was Newton's method solving algebraic equations, two completely different things. So that was up to now. And Riemann's definition of the definite integral looks like something completely different, but surprisingly enough, it gives the same results when both exist. So consider first the geometrical interpretation of this number. If we have a continuous function f, which is positive, so that it's easy to sketch, then this integral, let's call it a, has the meaning of the area of this region. Now, we can divide the interval AB into an equidistant by an equidistant grid of points. We consider the points x0 is A, and for some n, we consider the step b minus a divided by n. This is very similar as what we have done when working with when introducing the trapezoidal rule and the Simpson's rule for approximate integration. Then the next point will be a plus h, x2 will be a plus 2h up to xn is b. And now, in each of these intervals, we choose a number C1, C2, C3, and C4. That means we choose a number C1 somewhere in the interval x0, x1, that was in the Czech literature. In English we write a square bracket. We take the value, we consider the value C2 somewhere in the interval x1, x2. In general, the point C sub k will be somewhere in the interval xk minus 1, xk. We don't specify the exact position of these points. It's somewhere in this interval. And then we evaluate the function at C1, at C2, at C3, and at C4. That means in each C sub k, we evaluate the function, this is this height, and we multiply by the width of the interval. That means if we take this height and multiply by this is this rectangle. Then we take this height and multiply by this width, and this is this rectangle. Going all the way up to here. And then we sum all these contributions for k running from 1 to n. And this is called the Riemann sum. And if the limit for n approaching infinity exists, then this is called the Riemann integral. It should be here, but let's write it here. And to stress that we mean the Riemann's integral, we write capital R in brackets in front of the integral sign. So this is the definition of the Riemann's integral. Let me repeat it once again. We have a function defined in the interval AB. We divide the interval AB by n plus 1 points into n intervals. And these points will be equidistant. In each interval, we choose some point k. We evaluate the function at each ck points, at each point. We multiply this height by the width of the interval, which is the total integration interval divided by the number of intervals. So this is the width of one single interval. So this product has the meaning of this area of one column. And we sum, we take all these areas together, and then we take the limit for n going to infinity. If n goes to infinity, then infinity, then h goes to 0. And we have an expression where we have a very large number of terms, and each of them is very small. And for many functions, this limit exists. Especially if f is continuous, then this limit exists, and then the Riemann integral is equal to the Newton's integral. So the question arises, what is it good for if they are equal? Not all functions are continuous. For some strange wild functions, it may happen that one of them exists and the other does not. And also for functions of two or more variables, we introduce double or triple integral in a high dimensional spaces where the Riemann's approach is much easier, perhaps the only possible, to define an integral of such a function. We will work with double integrals in the next semester.